Hi everyone, we're continuing with the central limit theorem, the CLT, for sums, but especially means or averages. In the beginning, we talked about this big daddy distribution D, which was the distribution for the result of one die rule. It was a uniform standard die distribution, a discrete uniform distribution. The probability of 1 was 1/6, and in fact, that was a probability for each of these values from 1 through 6. Discrete uniform, 1/6 apiece. The mean of this distribution, mu, was 3.5. From either the zigzag, or because this was discrete uniform, you could just add these up and divide by 6. Also, the standard deviation was about 1.7. That was discussed in optional handwritten notes in lesson 16. For now, take that on faith. Now, when we consider the spike plot for this probability distribution, it's sort of taking the place of a probability histogram. The spike plot has a flat top. We have flat tops here, right? Discrete uniform. Probability of mass 1/6 for the integers from 1 through 6. That's if the sample size is 1. If you have one student, that student rolls a die once. Here's the probability distribution. But what if instead of one die, the student rolls 2 dice, say a red die and a green die? What's the probability distribution for the average on the 2 dice, the sample mean of the 2 dice? The 2 dice represent a sample. It's a sample of size 2 from this big daddy distribution. The probability distribution for x bar, if you have 2 dice and we're considering their average value, looks triangular, like so. Now, like for this big daddy distribution, the mean of the distribution of sample means is at 3.5. Here's 3.5 over here, which is the same as the mean for the big daddy distribution, 3.5. But notice that the spread is decreased here. It appears that these average values from 1 through 6, it appears that these average values are more tightly clustered around the 3.5 here in the n equals 2 case than over here in the n equals 1 case. It appears that the standard deviation of the x bar distribution has decreased as we go from n equals 1 to n equals 2. And that does seem to make sense. So the sampling distribution for the x bar distribution, that's where we have n equals 2 dice. The mean for the x bar distribution, mu sub x bar, was big daddy mu, 3.5, the same as for 1 die and its distribution. The standard error, or the standard deviation for the x bar distribution, is given not by sigma, the big daddy standard dev, but by sigma over the square root of n. It's the big daddy standard deviation from the original 1 die distribution divided by the square root of n. So the standard error, about 1.2 here, is going to be less than the original standard D for 1 die, which was about 1.7. As n increases, as the sample size increases, as more dice are rolled, from 1 die to 2 dice to 4 dice to 2 million dice, the standard error, the spread, will decrease, and we're going to see greater clustering around the 3.5. Again, sigma sub x bar is also called the standard error, or SE, of the mean. As the sample size little n increases, the standard error, or the standard dev of the x bar distribution, sigma sub x bar, decreases. Notice that the probability of mass for the triangular distribution is more tightly clustered around x bar equals 3.5 here for n equals 2 than for n equals 1. That's what we saw over here. We had greater clustering around x bar equals 3.5 over here than over here. Here we had greater spread. So in the n equals 2 case, the average of the dice is more likely to be close to 3.5, the mean of the original distribution. There is tighter clustering. Now as n, the number of dice in the sample, increases, what's going to happen to the shape of the sampling distribution, or probability distribution, for x bar? Okay, here's n equals 1 die. Here's n equals 2 dice. What happens if we go to 4 dice, 8 dice, and so forth? Well, for one thing, we're going to get less spread. We're going to get greater clustering around the 3.5. But also, look at the way that the shapes are changing. We started with a flat top uniform distribution for n equals 1. For n equals 2 dice, we got this triangular distribution. Take a guess. As we go on to 4, 8, 16, 32 dice, where we really make it official, what shape do you think we're going to approach? The shape of the distribution of sample means, the probability distribution of means. What shape will that approach? It's right here. Normal. We're going to approach a normal. 4 dice. Tighter clustering around 3.5 is looking a lot more bell-shaped. 8 dice, n equals 8. Even greater clustering around x bar equals 3.5, even more bell-shaped. N equals 16, even tighter clustering about 3.5, less spread. Standard error is decreasing, even more bell-shaped. N equals 32, very tight clustering around 3.5, very, very bell-shaped. In fact, by the time n gets past 30, like 31, 32, and so forth, it's official. We can call this approximately normal. It turns out that the CLT, the central limit theorem for means or averages, will say this. There is also a CLT for sums, but we're not going to focus on that as much. We're going to focus more on the central limit theorem for means or averages. I'm going to formally introduce this in just a moment. I'm going to tell you the result here first. In the case of n equals 32 dice, what happens if you, or if a machine, let's say, rolls 32 dice with Crayola colors? Then the distribution of sample means will be approximately normal. Hey, this looks pretty bell-shaped. Approximately normal, where the mean is Big Daddy mu, 3.5, the same as for the original distribution over here. It's 3.5. You're centered around 3.5 for all of these cases. The mean is 3.5 for all of these cases. But the standard error, that is the standard dev of the x-bar distribution, it decreases. As n increases, sigma over root n decreases. For n equals 1, it was about 1.7. For n equals 2, it was about 1.2. By the time we get to n equals 32, we're down to about 0.3, a lot lower. But I claim that the CLT for means or averages gives us this result. This distribution you're looking at here, where you're using this x-bar scale, this distribution will be approximately normal, it sure looks bell-shaped, with mean 3.5 and standard deviation, or standard error, about 0.3. Again, that's the distance between the mean line, I should move this a little bit, between the mean line and either inflection point. It's about 0.3. Seems to make sense. Okay, now going backwards, what is the central limit theorem? What is the statement of the central limit theorem for means or averages? Now, I wouldn't expect anyone to memorize this, but I would expect you to apply this in problems. All right. Again, doing a review of 32 dice, then we'll get to the general statement of the theorem. Actually, we may wait a while, like a few days, until we get to the statement of the theorem. But going back to 32 dice, let's do a recap. The central limit theorem applies when. So I'm kind of introducing bits of the theorem. When does the central limit theorem, the CLT, officially apply? When the sample size, little n, is large enough, and usually the standard is when n, the sample size, is bigger than 30. Now, this is not the result of some formula or algebra. It's just the result of common observation and practice. This is something that pure mathematicians get nervous about, the fact that this does not come from a formula. It comes from observation, from practical observation. In fact, if you look in the case of a die, we get pretty bell-shaped even by 4 or 8, it looks like, even by 16. Certainly by 16, it looks fairly bell-shaped. All right. But n greater than 30 is the standard. So you can have any shape distribution at the beginning. Flat top, it could be really messed up like that. By the time n gets past 30, we can assume a normal approximation will work out. Now, the central limit theorem also applies when the original distribution, Big Daddy D, is approximately normal, regardless of the sample size. Now, over here, since the original distribution was not bell-shaped, we had to wait a while. Maybe not so long, but to make it official, we waited for n to be greater than 30, for the sample size to be greater than 30, before we could officially say that we have about a normal distribution here. Although, yeah, it looked pretty normal even before that, like at 16 even. But if the original distribution is bell-shaped, I'll erase this. What if we have a bell-shaped distribution? Like so. What if we have a bell-shaped distribution? Then the CLT basically kicks in immediately, even at n equals 1. You don't have to rely on a large sample size. If you start with a bell shape, you're dealing with bell shapes all the way, normals. The CLT applies when the original distribution is approximately normal, regardless of sample size. So there are two cases where the CLT applies. Okay, if the sample size is large enough and is greater than 30, regardless of the shape, or regardless of sample size, if you start with something that's roughly normal. So basically, if the sample size is big enough, or you start off normal, then the CLT will apply, and you're dealing with normal distributions with these parameters, mu and sigma over root n as your standard error. According to the CLT for means, if a machine rolls 32 dice, n equals 32, then the sampling distribution for x bar is approximately normal. Okay, this is the same guy I showed you before. Let's describe him. The sampling distribution for x bar has, as its mean, mu sub x bar, is the same as the Big Daddy mean, mu, for the original uniform distribution, 3.5. The mean is 3.5. The mean of the mean distribution is 3.5. The standard error, or the standard dev of the sample mean distribution, is not sigma, but sigma over the square root of n. Big Daddy sigma, for the uniform distribution, it was about 1.7078. I said that up here. But you have to take that 1.7078 and divide it by the square root of 32, which was between 5 and 6. This fraction ends up being a lot less, about 0.3. 0.3 is way less than 1.7. It's about a fifth or a sixth of 1.7. It's way down. So we're getting much tighter clustering of this distribution about the 3.5 here, the mean, as opposed to up here, where it was a lot more spread out. Here's a lot more spread out. Standard dev here was 1.7. Standard dev down here, 0.3. All right, so the CLT for means tells us this result, that the sample mean distribution was approximately normal, with mean mu sub x bar, same as Big Daddy mu, 3.5. Sigma sub x bar is not Big Daddy sigma, it's not 1.7, it's more like 0.3. I like to write out 5 sig figs just to be safe. So basically, we expect the sample mean to be very close to 3.5. If a machine rolls 32 dice, we expect the sample mean to be very close to 3.5. And why is that? Well, think about it. If you have a machine rolling 32 dice, or better yet, imagine a machine rolling 1,000,000 dice, n equals 1,000,000. What do you expect to see? You see 1,000,000 randomly thrown dice on the ground. What do you expect to see? A big mess, right? But what do you expect to see? You expect to see about a sixth ones by the law of large numbers, about a sixth twos, about a sixth threes, about a sixth fours, about a sixth fives, about a sixth sixes. So it's kind of like uniform. So you kind of expect, kind of a uniform distribution between ones through sixes, right? But what about the average? What's that going to tell us about the average? Well, we have about a sixth ones, about a sixth sixes. The number of ones and the number of sixes should closely balance each other out for 1,000,000 dice. So don't you think the ones and the sixes will basically balance each other out? And what do they balance out to? What do they average out to? 3.5. What about the twos and the fives? You should have about equal numbers of those. Again, they'll tend to balance out towards 3.5, strongly so. What about the 3s and the 4s? Well, they'll average out to 3.5. But that's why we expect the sample mean to be very close to 3.5 if we have many dice, because we expect high and low numbers to have a strong tendency to balance each other out. So for example, the 1s and the 6s will balance each other out, the 2s and the 5s, and the 3s and the 4s. So we have a strong tendency for the average overall to balance out to 3.5. We have strong balancing effects, The standard error is about 0.3, which is way less than the 1.7 that we started out with for Big Daddy Sigma. The standard D for the original uniform distribution, n equals 1 die. So that was an application of the CLT to the case of 32 dice. As I promised, next time, it could be a few days from now, next time, we're going to see the statement of the CLT and see where all this stuff came from. Until then.